How's it going, accelerated chemistry students? This is Mr. Spurk, and this is your chapter 15, section 1 notes all over water and its properties. So we're going to look at water in the liquid state. Water, or H2O, is a simple molecule consisting of three atoms. Covalent bonds hold the oxygen and hydrogen together, and oxygen is a highly electronegative atom, so it becomes partially negative because it pulls harder on the electrons in the bond. These are all things we've talked about before. Thus, the OH bond is highly polar. So, if you remember, when we draw out the water molecule, we know that water is bent and has two lone pairs, and we know that water is highly electronegative, so it's going to pull and have that partial negative while leaving the hydrogens partially positive because it's pulling a little bit of those hydrogens away. And we know that if we have another water molecule, it's going to undergo the same thing, partial negatives and partial positives. And then this is where we see our hydrogen bonds. Remember, we see the partial negative O wanting to bond to the partially positive hydrogen, and the same thing here. And those are our hydrogen bonds. In general, polar molecules are attracted to one another by dipole-dipole interactions. The negative end of one molecule attracts the positive end of another. However, in water, we know this results in hydrogen bonding because of the high electronegativity of the oxygen. Many unique and important properties of water, including its high surface tension, low vapor pressure, and high boiling point, result from these hydrogen bonds. As you can see here, and as I'm sure you've seen in your everyday world outside of school, water forms beads or droplets. That's because of that high surface tension, all caused by those strong hydrogen bonds. So for surface tension, the water molecules within the body of the liquid form hydrogen bonds with the other molecules that surround them on all sides. Water molecules at the surface of the liquid experience an unbalanced attraction. As a result, the water molecules at the surface tend to be drawn inward. So basically that central water molecule in the center is trying to pull on all of those, which pulls them into the spherical shape. The inward force or pull that tends to minimize the surface area of a liquid is called surface tension. Water has a much higher surface tension than most other liquids. It is possible to decrease the surface tension of water by adding a surfactant. A surfactant is any substance that interferes with hydrogen bonding between water molecules and thereby reduces the surface tension. Things like soap and detergents are our common surfactants. So we're going to go back a chapter or two and talk about vapor pressure. And hydrogen bonding between water molecules also explains water's unusually low vapor pressure. An extensive network of hydrogen bonds holds the molecules in liquid water to one another. These hydrogen bonds must be broken before water changes from the liquid to the vapor state. So the tendency of these molecules to escape is low and evaporation is slow. So for the boiling point, molecular compounds of low molecular mass are usually gases or liquids with low boiling points at normal atmospheric pressure. Ammonia, or NH3, has a molar mass of 17 grams per mole and boils at about negative 33 degrees Celsius. Water has a molar mass of 18 grams, but it has a boiling point of 100 degrees Celsius. The difference between the boiling points of ammonia and water are due to the hydrogen bonding, which is more extensive in water than in ammonia. Even though we have one of the NO or F, which we can have to have hydrogen bonding, ammonia already has 3 hydrogens to it, so the nitrogen isn't as partially negative as the oxygen is in the water molecules. And the geometry of the NH3 isn't as conducive to grab onto other NH3 molecules as the bent water shape is. So if we look at water in the solid state, ice cubes float in your glass of iced tea or whatever else you're drinking because solid water has a lower density than liquid water. As water begins to cool, it behaves initially like a typical liquid. Below 4 degrees Celsius, water no longer behaves like a typical liquid. This is highly unusual for liquids. As water begins to cool, it behaves initially like a typical liquid, and when the temperature falls below 4 degrees Celsius, the density of water actually starts to decrease. Ice, which forms at 0 degrees Celsius, has about 10% lower density than water at 0 degrees Celsius. Ice is one of the only few solids that floats in its own liquid. Why is ice less dense than the liquid? The structure of ice is a regular open framework of water molecules in a hexagonal arrangement. The unique properties of ice are a result of hydrogen bonding. The fact that ice floats has important consequences for all organisms. Extensive hydrogen bonding in ice holds the water molecules farther apart in a more ordered arrangement than in a liquid. The liquid at the bottom, so the reason it's important for other organisms is because the liquid water at the bottom of an otherwise frozen body of water is warmer than 0 degrees Celsius. So the fish and the other aquatic life are able to survive. If ice were denser than the liquid water, bodies of water would tend to freeze solid during the winter months, destroying many of Earth's organisms. So in review, many unique and important properties of water, including its high surface tension, low vapor pressure, and high boiling point, result from hydrogen bonding. The structure of ice is a regular open framework of water molecules in a hexagonal arrangement. And that's it for Chapter 15, Section 1. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, the resources CD, and pearsonchem.com. Have a good day, guys.